Okay. All right. Strongest substances on the planet. I could say the universe, actually. But no one cares. But we don't live out there, so. If this is true, what does that mean? Give me another property. How do we know it's strong? No, they break easy, actually.
Brittle. I'm just throwing things out there. I don't really know.
Atoms, there's a lot of them.
High. Actually, very high. Should write very high. Melting point. Very high melting point. Diamond melts at like 2,800 degrees Celsius. Salt melts at 800. Salt's ridiculously strong. 800 degrees Celsius is really hot. Diamond laughs at that. 2,800 for diamond. Okay? So very high melting point. So examples, diamond, which is basically just pure carbon. It's carbon solid. Diamond is the most common example of a network solid. So when you say network solid, technically it's called network covalent. I don't want to confuse you.
Wait, what's this say C?
Oh, carbon solid, little s. But yeah, network solid, network covalent solid means the same thing. So yeah, diamond. Did you know we can make diamonds in labs?
The peanut butter. What?
What did you just say about peanut butter?
Make it with peanut butter.
You can make diamond with peanut butter.
Yeah.
Because it's a source of carbon, right? All you need is a source of carbon. And
You gotta press it really.
you need a lot of pressure, need a lot of heat.
What? Just go proceed.
I don't know what you just said, but okay. So yeah, we can grow diamonds in labs. Now, those diamonds
Fake.
are very
Fake.
pure. There's no impurities. We can. You ever hear like? I have it up here.
No whining.
The four C's of diamond. Diamonds. Anyone? Okay. Cut, clarity, color, something else.
What are you talking about? You're talking about seas like the ocean.
No. If you're gonna go buy diamonds, all right. I don't know about this really, but jewelers will be like, all right, here's the 4 C's: how it's cut, how clear it is, the clarity, the color of it. I don't know, whatever. But the point is, stay with me. When you make a diamond in a lab, you can make all that very, very perfect, and you get like these perfect, humongous diamonds. They're worth less than the real diamonds. Why?
Because they're fake.
Not natural.
Right.
Synthetic.
Right, pure. The pure that is because it's fake is actually lowering its value. Real diamond have impurities which make it more rare. And also, did you know? Well, diamonds are expensive. You know that, right?
Yeah.
Do you know why they're expensive?
Because aren't they like?
Well, they're supposed to be rare. Things that are rare.
They're not renewable? Nope, I lied. Just
Well,
kidding. Don't.
it takes for. I'm not judging. It takes a long time for them to be formed. So no, they're not. What did you say? I forgot you said it already. Right, they're not.
So I was.
What makes them expensive?
Diamond company.
Explain, Trevor.
There's like a monopoly over diamonds. I don't know the company.
They have
Well,
giant
in
warehouses
Africa
full of-
and Russia, there's a lot of diamonds.
They only release
And
a
they
certain
only
amount.
release a certain amount on the market.
They're-
Otherwise, if you flood the market with diamonds, then they'd be worth nothing. But so a lot of people think there are, just a little bit of diamond,
No,
just a
there's
few in the
crap.
world. That's why it costs so much. I think people just think that to make them feel better about their diamond. But there's actually a lot of diamonds in the world.
Yeah.
Well, some of them.
And a lot of them, this has nothing to do with chemistry, but just more like ethics, a lot of them are from mines in Africa where the people are treated horribly. So you ever hear of blood diamonds?
Yeah.
Yeah, it's because people died and they treat the people terribly. They cut their arms off and all types of crazy things because all they care about them is mining diamonds. So you can actually go to a jewelry store and say, where's this diamond from? And you can trace it back so you're not buying diamond that some little kid died for to mine. So you don't want to support that kind of company.
Where would you
We
find
can already tell you about the baby goers.
I don't know if there are any. Maybe there are. I don't know. Okay, up here. Back here. Now, diamond is one. Another one, quartz.
Quartz.
SiO2. That's the chemical formula for quartz. SiO2. It's also sand. If I order sand, I know that sounds crazy, but I'm not going to a beach and just
Go to your
stealing sand.
child's little sandbox.
But I don't have a sandbox. So sand is pure quartz, SiO2, just ground up. It's very, very strong. And the other one that you probably won't know is SiC. It's called silicon carbide. Those are the 3 that you will see on the Regents if it says, which of the following is a network solid? There's your 3. They won't say quartz. Well, I shouldn't say won't. I doubt it. They'll put SiO2. They will put diamond, and then SiC. The only other one, put a star. It's not really a Regents thing, but I want to be honest with you here. Graphite. Now, it's confusing because graphite is soft. It comes off on your finger. We can write with it. It's pencil, obviously. So this is kind of, what's the word?
Confusing.
Yeah, there's an anomaly, sort of, is what I'm looking for. So parts of the graphite have this. The other part is kind of weak. So it's hard to explain. I'm not going to get into it because it's confusing. Just remember these 3 here, okay? Those are the main network solids. All you need to remember is that these are really, really, really strong, really high melting points, and that they're network solids. So that's really it. There's not a whole lot of notes here. The only reason that this is strong, this may or may not make sense to you, these things here have no forces of attraction. What does that mean? They only have bonds. So why would that make them stronger?
Bonds are stronger than forces.
Right, bonds are stronger than forces. So I use the analogy of shaking hands. You want to shake my hand, Monica? This is a force of attraction. I can let go. That can be broken easily. Okay, stay with me, stay with me. Bonds, if you remember I talked about this a long time ago, the bonds would be like what holds me together. So if I said Annika, rip my arm off my body, she can't. It's too strong. The attachment is too strong. Bonds are strong. Shake my hand. Forces are weak. I can let go, she can let go, that's weak. These things, that would be like, one more time. We're shaking hands and all of a sudden we grew just one arm together. Yeah, well, for many reasons. So that is what these are like. It's a weird example, but stay with me. These diamond, quartz, silicon carbide, they don't have forces. There's none of the handshaking. So imagine if all of you were connected. That's why it's so strong. Okay? Yeah, it's weird. It's weird. Siamese twins. Okay? So that's why these things are so strong.
Wait, is it wrong to just call them network solids?
It is not.
You have to say, okay.
Yeah, network solid is good enough. You don't have to say network covalent solid. All right.
So they're not actually covalent. No. They are? What the
They're
heck?
not. They're not covalent. They're not covalent. They're network covalent. They're different. They're not what you learned. All right. Okay, here we go. Write this down.
For a new thing?
Nope. Bonds ranked by strength. Let's start with the weakest on top. You just learned 4 different types of bonds. 5, technically. Give me the weakest type of bond. I'll give you a hint, and they only exist as gases. Covalent is weak. Specifically, which one is the weakest? Nonpolar is the weakest. Nonpolar covalent is the weakest. Honkobriffs. They're all gases except for Br. Oh, and iodine, but it's sublime's real easy. So nonpolar covalent, they are the weakest by far. Really low melting points. What's next?
Polar
covalent. That's like water. Polar covalent, we'll just say, is weak. What's next? It's ionic and metallic come next. Sometimes they overlap. I'm going to write metallic first. Oops. And then ionic. So all we need to know is that both of them are strong. They're both strong. They're strong bonds, pretty high melting points. You don't need to know the order there. Just need to know that they're stronger than these two. And then what's next? Network solid, right? So network solid would be the strongest. So what do you need to know on the Regents or on a test? Which of the following has the highest melting point? They might give you a polar, a metallic, and a network solid, and a nonpolar. They might give you one of each. All right, there's only 4 choices, so someone's left out. But they'll give you one of each. You're looking for that one. Now, if they give you 4 covalents and 1 ionic, then you're looking for the ionic. So it is important to kind of have a general idea here. Covalents are weak. Metallic, ionic come next, and then these are, it's not even close. They're way, way stronger than these. Okay? So network solid, the strongest. So that's a typical question. Here's another question. Raise your hand if you know. Which one conducts electricity as a solid? Raise your hands. Which conducts electricity as a solid? Got a 20% chance of just straight up guessing.
Yes, but
Andrew.
I don't want something that way.
Metallic, yeah, metallics conduct as solid. Okay, raise your hands. Which one dissolves in water very easily? Which one dissolves in water very easily?
Oh.
Trevor.
Oh, well, I hate
Polar.
Very good. Like dissolves like. Good. What else could dissolve in water? Ionic might, depending on the ionic, because of the partial charge thing. Like dissolves like. Similar forces. Good. Which one will not dissolve in water for sure? There's three choices here.
Okay.
You know, he's just not
No,
going to
can I
pick
choose
the
one?
first
One. Nonpolar will not dissolve in water. Give me an example. It was on your test or quiz yesterday. And remember that question? It was a multiple choice. Oil. Oil is nonpolar. The one on the test was hexane. Hexane is nonpolar. What's the other two that will not dissolve in water? Right. Diamonds don't dissolve in water. That'd be crazy. If it rained out, people would be freaking out. Okay? Cover your diamonds. What's going on? Okay. What else? What's the other one that will not dissolve in water? Yeah, metals don't dissolve in water either. Again, that would be a problem for cars when it rains.
Water can speak of
Oh,
oxidation.
which one conducts electricity as a liquid? There's two answers. Joven. Ionic and? Yeah, guys, mercury. Have you ever seen mercury?
Yeah, it's like silver.
Yeah.
It's really weird looking.
It is weird.
I saw it in a thermostat in an old
Metallic, mercury, if you put it, so when you put water in a graduated cylinder, what does it do?
Yeah, right.
You want to read the volume, what do you have to read? The meniscus goes like this, right?
Man, this
Right, goes down, kind of looks like this.
Mercury do the other thing?
Yeah, mercury goes like that. Yeah, why?
because it's got strong power.
Stronger bonds, stronger forces, right. Which one conducts electricity in water? Ionic. Who said that? Good. That's the type of stuff you need to be ready for on the regents. Not only knowing, stay looking forward, not only knowing the difference between all of them, but answering questions about the properties. So we spent a long time on the unit, I feel like, because there's a lot to learn. Hopefully you are pretty good with that. All right, I've been grading some of the quizzes. They're okay, I'll say.
No.
Okay. All right. Now, moving on. What does this prefix mean?
Intra.
Intra. Versus, what's inter mean?
Inter is inside.
Here we go again.
Between the
Inter, right here. Intra. Holding my arm together. Okay? Intra is inside here. What's inside here holding my arm on? Bones, muscles, ligaments, tendons. That's intra. The handshake is inter, between. So you got to really remember that for this. Write this down, new notes. Intermolecular forces. Intermolecular forces of attraction. Okay, so I'm going to do as much as I can in about 5 minutes here. I know we're doing a lot of notes, so stay with me. You're doing a good job. Intermolecular forces. Van der Waals forces. That I like to call, for Star Wars fans, the Force. Is the Force. It holds everything together. Literally everything in here has this. Okay? Van der Waals force. Another name for that is called London dispersion forces. London dispersion forces. Now, before I get into the specifics, we got to really make sure we know what this word intermolecular means. So underneath here, draw a picture. Actually, we'll draw, we'll do H2. So H bonded to an H, dot, 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 dot. Another H bonded to another H. That dotted line is the intermolecular force. Inter means between the two molecules of H2. This bond here is called the intramolecular bond. So So that line we learned is a covalent bond, a nonpolar bond, but that's inside the molecule. Outside the molecule, the handshake is the dotted line. It's really easy to break the dotted line, not easy to break that bond. So intermolecular is between molecules. It's really important to understand that. If you want to circle these maybe, if that helps you understand that that's kind of like one thing on its own, that's one thing on its own, and then in between them, that's called Karen, stay with me.
I'm here.
Intermolecular force, that's in between. That is what's broken. Oh yeah, you gotta go. Yeah, we don't have any homework.
Okay.
Oh wait, sorry, I wanted to hand this out. Quick, come here. This is practice for Friday.